Welcome everyone to today's Explainer. Okay, let's dive right into this because today we're tackling a force that literally holds the entire universe together. We're talking, of course, about gravity.
But, before we get too deep into the physics of it all, I want you to ask yourself, is gravity just a force that makes things fall down? Like you drop your keys, they hit the floor. Boom. That's gravity, right? Well, yeah, sure, but if you think that's the whole story, you are in for a massive surprise. Gravity is so much more than just this downward pull in everyday stuff.
To really get a grip on it, let's look at the actual definition. Gravity is a fundamental force that attracts any two objects with mass to each other. Basically, if it has mass, it's got gravity. But take a close look at the second part of that definition. It says it even attracts energy. Now, that is a totally mind-blowing concept that goes completely against what most of us learned in basic science class, right? Hold on to that thought because we're absolutely going to unpack how gravity pulls on massless energy a little later in this explainer.
First, let's just ground this in our everyday reality. Look around you. Gravity is quite literally everywhere. It's the very reason we're standing stable on Earth right now instead of just floating off into the atmosphere. But it scales up dramatically. Zoom out into space, and it's the exact same force keeping all the planets revolving around the sun. The sun's massive gravitational influence reaches way out and holds the entire solar system perfectly in its orbit, keeping everything moving dependably right on track.
Section 1. A universal attraction. Let's move to Orion and see how this builds on a much grander, universal scale.
What's really fascinating here is that gravity isn't just a sort of maintainer of the universe. It's actually an active creator. Think about how our sun was born. Billions of years ago, all these particles, molecules, hydrogen atoms, they're just hanging out, concentrated together in space. Then gravity kicks in. It starts pulling these particles inward, tighter and tighter. That intense, relentless pull created so much pressure that nuclear fusion finally ignited. So without gravity literally forcing those atoms together, our sun, and by extension, all life on Earth, well, it simply wouldn't exist.
Now let's bring it back down to a micro scale for a second. Because the rule literally says any two objects with mass attract each other, that means everything. You, personally, are gravitationally attracted to the chair you're sitting on right now. And, believe it or not, your chair is gravitationally attracted right back to you. I know it sounds a little silly, but it is scientifically accurate. Size honestly doesn't matter for the basic rule here. If it has mass, there is a mutual attraction going on.
And from the chair in your room, let's leap across the cosmos. 2.5 million. That is the distance in light years to the Andromeda galaxy. Why does this matter? Well, because nestled in the center of that incredibly distant galaxy is a supermassive black hole. And thanks to the universal nature of gravity, that black hole, which is 2.5 million light years away, is gravitationally attracting us right now. And we are attracting it. Literally every single thing in the universe is connected by this invisible web.
Section 2. Newton's two rules.
Now, obviously, a pull spanning millions of light years isn't something we actively feel in our day-to-day lives. To understand why, we've got to look back to the 17th century, to Isaac Newton. He made some absolutely groundbreaking observations that established the rules of the game for how gravity operates. So the crucial point is that the strength of this gravitational pull comes down to just two main factors. Observation 1 is the object's mass. Simply put, the greater the mass, the stronger the pull. Observation 2 is the distance between those objects. As you can probably intuitively guess, the further away things get, the weaker that connection becomes.
Let's dig into that first rule about mass. Think about this number for a second. 99%. The sun is unbelievably heavy. Actually, scratch that, heavy isn't even the word. It contains an astounding 99% of the total mass of our entire solar system. That's insane, right? Because its mass is just overwhelmingly huge compared to all the tiny planets, its gravitational pull is absolutely dominating. That is exactly why the planets are locked into orbiting it. Bottom line, the more mass you bring to the table, the more gravity you generate.
Section 3. The power of distance.
But what about that second rule? Let's explore what actually happens when objects move further apart. Imagine, just as a thought experiment, what would happen to the gravitational pull between the Earth and the Moon if the distance between them suddenly doubled? You'd probably assume the gravity would just be cut in half, right? Makes sense. But nope. Because of how distance mathematically affects gravity, if the Earth and Moon were twice as far apart, the remaining gravitational pull would drop drastically, all the way down to just 25%. A massive 75% of that gravitational force would just be lost. Distance dilutes gravity incredibly fast. And speaking of the moon, it is the perfect example of how gravity works across a massive distance, even when it's completely invisible to us. Look, we don't physically feel the moon pulling on our bodies as we're walking down the street, but we can undeniably see its gravitational influence. The ocean tides are direct proof of this. The high and low tides, the shifting, rhythmic behavior of the waves, that is all completely dictated by the moon's gravitational pull reaching across empty space and tugging on Earth's oceans.
Section 4. Bending massless light.
All right, now let's completely shift the paradigm here and circle back to that wild teaser I threw at you at the very beginning of this explainer. And this brilliantly illustrates the true, profound power of gravity. It's time to talk about bending massless light. On one hand, we have massive objects, right? Stars, supermassive black holes, things with immense, practically incalculable weight. And on the exact opposite end of the spectrum, we have massless particles. Think about a simple ray of light. The particles in light, called photons, have absolutely zero mass. Zero. They are pure energy. So, according to the simplest definition of gravity, they shouldn't be affected at all, right?
Wrong. Turns out, gravity is highly capable of bending a perfectly straight beam of light. If you were to shine a beam of light perfectly straight so it passes really close to the sun, the massive gravity of the sun will actually pull on it and literally bend its path. This completely flips how we view gravity. It proves that gravity's influence isn't just restricted to things with mass, it actually affects things that carry pure energy. Even completely massless light cannot escape a strong enough gravitational pull. Nowhere around it.
Section 5. The ultimate mystery. Talk about a massive conceptual leap, right? We've gone from dropping keys on the floor to understanding how stars are literally born and how light itself gets warped by invisible forces out in the vacuum of space. As you absorb all of this, you really have to ask the biggest question of all. Why does gravity actually do this? Why do masses just inherently pull on each other across the entire universe? Why on earth does light bend? I mean, it's pretty easy to describe what it does, but why? Well, I promise you, it isn't magic. There's no mystical force at work here, without a cause. There is a deeply valid, mind-blowing scientific reason why this all happens, and it's a reason that Albert Einstein brilliantly proved. But to dive into Einstein's absolute game-changer of an explanation for how gravity actually works under the hood, well, you'll just have to join me for our next explainer. So keep wondering,